In this video, we're going to talk about infrared spectroscopy and how you analyze that to use the type of and see the type of bonds that are in a molecule, a covalent molecule. So, first of all, what is infrared? Infrared is any radiation within that frequency, but don't worry, you don't need to remember that. It causes vibrational energy changes in the chemicals over quantized energy levels, and that doesn't really matter too much either, but all it means is imagine the molecule is shaking like this, okay? And then it has to go from level 1 to 2. So then it will shake even harder, and then it will 3, and I'm not going to shake that hard, but it basically goes up set levels. It won't go 1.5 times harder, 2.5, it'll just go 1, 2, 3. Now that's a simplification, but that's what vibrational energy changes are. Now, those involve different types. So you can imagine these are carbon dioxide, or just basically an atom surrounded by two other atoms. You can see that one atom is going further away, and then the other one's going further away, and it's asymmetric, as in it's not balanced. There's no balance there, right? And then we go for the next one, symmetric stretch. So, and that means the bonds are getting shorter, then they're getting longer. Okay, and then we go for the bend, which is like that. Okay, and all those things can happen in molecules. And what they do is they all absorb different radiation, different frequencies. And if they absorb different frequencies, we can actually see what they are. We can see what the bonds are. So there's our three types, our asymmetric, our symmetric, and our bend. But again, you don't really need to know this. It's just a basis for what's going on. Now, how it works, and again, this is not really assessed, but you have to know it to kind of understand the rest. Infrared source. So we get our infrared light, and I've simplified this massively because you don't need to go over it in a complicated way. And then the infrared goes through two different ways. So you can go through the sample that you provide, so you put a little bit of sample in, and then you get the infrared going through it, okay? And then also you have a background and or a reference. So the reference might be you want to compare this compound to this compound. So you have pure paracetamol, for example, and then you have paracetamol you've made, and you can compare them using a computer if you have that reference. The background is usually air, because you don't want the spectrum from air. Now this doesn't make a huge amount of sense at the moment, but we'll move into the spectrums in a minute. Because what happens is it analyses what infrared is actually absorbed, okay, and what is transmitted, what goes straight through, and then it gives you a spectrum looking like this at a detector. And these peaks that you have that are going down, they're where the infrared has been absorbed. And we can tell the type of bonds within a molecule by looking at these peaks or troughs. Okay, now, if that's the case, let's look at what one of these looks like. We have transmittance, and transmittance basically just tells you how much infrared is actually absorbed. So if 100% is transmitted, then we must be absorbing some here. Now, we use wave numbers instead of wavelength. Now, wave numbers, the number of waves found in 1 centimetre. So you calculate it just by doing 1 divided by the wavelength. Okay, but again, you don't need to really remember that. You just need to analyse the spectrum itself. And you don't need to really go on about this or remember this, just analyse the spectrum itself. So, if that's the case, like I said, across the top here, no IR is absorbed, it's all transmitted. Okay, so that means 100% transmittance through the molecule. Then we go from here and we look at the fingerprint region. Now, tip my head up here. So we've got the fingerprint region here, and that's usually very complicated and very messy. So it's usually analysed by a computer. And it can be used to identify the molecule, but they do that in industry. We don't do it at A levels. So don't worry about it too much. But if there is something in the fingerprint region and you can't identify a molecule and you're thinking, oh, okay, I'm not really sure, look in that fingerprint region because sometimes they can make it very obvious there's a peak there. And I'll show you how to do that now. So to do this, you need to use the datasheet. And on the datasheet is an infrared table. And that's why this is not one of the most complicated areas. There is an infrared table here that shows you all the bonds and then tells you what kind of bonds they are and tells you what the wave number is. So the wave number range is over there. So if you see a peak that comes in between those wave numbers, it's most probably going to be one of these bonds. There is a little bit of overlapping, but I'll show you how it's actually quite obvious if you do it the way I show you. Now, if you look at this molecule right here, you can see types of bonds. A C double bond O, okay, a CC and a CH. So there's the CC, there's the C double bond O, there's the CH. Now the CC is in the fingerprint region, and it's in almost every single organic compound, and therefore we generally don't look at it, and you don't quote it, so don't worry about it. The CH is the same. All organic compounds tend to have CHs on them. There might be the odd exception, but the ones you're going to come across all have CHs, and therefore the CHs we don't report either. We don't put those on our answers because the CH itself is in everything, so you can't differentiate anything. The C double bond O can differentiate things, so we always look at that one. So the ones we look at generally are C double bond O and the OHs. And in your first year of A level, you'll do OH, and the second year you might come across some NHs, but the first year definitely just OH. So if we're looking at these, let's keep this by us. So if you stop the video right now, open up the datasheet or have a paper copy of the datasheet so you can use it as we're going along. So here we have our propanal infrared spectrum. Wave numbers go from 500 to 4,000 transmittance up here. You can see these peaks, and these are due to symmetric stretches or asymmetric stretches or bends, and that's why you can get multiple peaks in the same place. What you do is you go down the center of the peak, and when you go down the center of the peak, you then go down with a ruler and you find out exactly what the wave number is. Okay, now if that is the case, we can look at two peaks here. No? So we've got the CH, and then we can see here that this is in the region for C double bond O. Okay, and we note down what the wave number is here. So if that is the case, and then we move on, we can analyse the spectrums to find out what type of bonds they are. And there's a certain way in which you do it. Now this is worth writing down in your notes. Always give the wave number at the centre of the peak. So this is one peak because you can see the base is all joined up. So this is one peak, you go down the centre, give the wave number of that. Then give the range it is in from the data sheet. So look at the data sheet, see where this comes, give that range. Okay, then state the type of bond and also state what is not there when you're differentiating between compounds. So if you want to, it says which of the compounds is this IR, and it gives you 4 different examples. You might have to differentiate by saying, well, that peak's not there, so it's not this molecule. Now, we'll go through examples of that soon. So we've got this up the top the entire time. We've got our propanal. Let's give some model answers. So we've got the 2 here, and let's give a model answer. Now we're only going to do one of them because we don't bother with the CH. So the peak at 1820 is in the region of 1630 to 1820 and is a C double bond O bond. Notice you're saying bond, you are not saying it is a aldehyde. You're saying it is a bond. Okay? And so that is the process that I want you to copy and do as you go through this video and through the worksheet. Our next example is going to be of a carboxylic acid. Now remember, in the exam you might get multiple structures and you have to differentiate between them, and we're going to go through examples of how you can differentiate between molecules using IR spectrum. Now, if you can do it on your own, stop it right now and just carry on and try and identify them using the techniques which we've shown you. So, what bonds have we got? We've got an OH here. How do we know it's an OH? Well, it's in the right region, okay? And there's this characteristic broad spectrum here, very broad. Now, you can also see these little peaks at the bottom. That's the CH that's just going straight through, so it's an overlapping, so don't worry about that if you see it. Okay, and you've got this broad thing, which is the OH. So if we do that in the way in which we're meant to, as in writing it out with the peak number, right down the centre, the range, and then what bond it is. We think it's in a carboxylic acid, and we'll tell you why now. So we think it's in a carboxylic acid because we can also see a C double bond O. That C double bond O is at 1750, in the right range, and so because we've seen both, we think it's probably a carboxylic acid, but we also think it's a carboxylic acid because this OH is in the region for carboxylic acids, whereas if this OH was an alcohol, it would be slightly later on. It would be between 3,200 upwards. Okay, and so you'd see a peak here instead, okay? And that is how you differentiate between an alcohol and a carboxylic acid. But we'll show you the alcohol one next so you can see that difference. I just want to show you one last thing to do with this, which is with the fingerprint region. Now, we know the fingerprint region is used with computers to compare, so you can see how pure a sample is. However, what you can also do is if there's an extra mark, for example, this is 1 mark, this is 2 marks. If you see it's 3 marks, they might be asking you to look in the fingerprint region for one other peak. So if that's the case, one of the most common ones to be looked for is this C single bond O. Now the C single bond O can sometimes be made very obvious by the exam boards, and if it is, you really should put it down. So add that in if it is there. Now that is how you do the IR of propanoic acid, and then finish it off with the CO answer. So with your peak number, your range, and your type of bond. So whenever you're doing this, remember, most important thing, look for the difference between the OH on a carboxylic acid and the OH on an alcohol, which we'll show you next. Our final example is going to be propan-2-ol. Now, it could be the same as propan-1-ol if you're looking for this. It doesn't really matter, but what we're looking for is an OH. So what you notice is that broad peak again, okay, and that is our OH. And there's our CHs right here. And you look at a few of these spectrums and they become really obvious. So the broad one is going to be our OH. Now we've also highlighted over here, and we have highlighted the fact that we've got a C single bond O there as well, but do not worry too much about that one. Okay, if we look at here, and then we take the middle of the peak is at 3,300, it's in the region of 3,200, 3,600. Notice it's moved slightly that way. And that means it's probably an alcohol. But the technique we want to show you in this one is to say what's not there. Remember, you've got to say what is there, but also, if it helps, you've got to say what's not there. So we would normally look in this region right here. So let me go over here. Okay, you would normally look at this region round about here for a C double bond O. Now that C double bond O, okay, is not there. You can see there's nothing there in that region. Okay, so we'd like to put a nice sentence there to say no peak between the region for C double bond O, so no C double bond O bond, so it's probably an alcohol because you only have an OH. And that's how you differentiate and write down your answers for analysing alcohols and, in previously, carboxylic acids and aldehydes. In our last part of our video, we are going to talk about the connection between infrared radiation and global warming and breath testing for those who drunk alcohol. Now, we have an atmosphere, and that atmosphere is affected by the gases within it. And the gases within it are changing, and they're changing because of human activity. And the Earth is warming up significantly faster than it should do, or than scientists believe it should do, okay, because of the human processes that we have. Now the processes that we have include burning fossil fuels, and we use them in our factories, and we use them in our cars, and we use them to heat our homes. We also use them to fly. Now, there are other problems. So we think of CO2 as a greenhouse gas, but CH4 is also a greenhouse gas. So we release CO2 from all of these other places, but we also have CH4 that's trapped in the ice cap, and then that will be released when it melts, and that's going to be a huge problem as well. We also have CH4 increased by our diet. So we have a meat-based diet, and if we don't move to a more sustainable meat-based diet, or we don't go vegetarian, we're also going to have a bit more problems. But how does that relate to infrared? So infrared works like this, and this is why it is a problem. Okay? Now, infrared comes from the Earth. It gets re-radiated out to the Earth. But first of all, the energy has to come to the Earth. And the energy comes to the Earth from the sun. So if I walk over here, you can see the sun is shining its radiation, okay, which is a huge amount of UV light and things like that, which gets filtered out by our atmosphere. But then some of it gets absorbed by the Earth and then re-irradiated by the Earth, okay, as infrared. Now, it gets trapped by the greenhouse gases. So the greenhouse gases are CO2, H2O, CH4 and others. Okay, but this relates to infrared because you know that CO2, H2O and CH4 absorb infrared radiation because otherwise infrared spectroscopy would not work. So it's the C-double-bond-O that absorbs the infrared radiation. It's the OH in water that absorbs the infrared radiation and the CH in CH4 that absorbs the infrared radiation. That stops it being released, which means the Earth warms up. Okay, so basically if we didn't have global warming, we couldn't have infrared spectroscopy, unfortunately. The two are intimately linked. Now, the application of infrared spectroscopy is breath testing. So ethanol is found in alcoholic drinks and it's got that OH bond in it. The IR absorption can be detected when taking that breathalyzer test. And the more intense the absorption, the higher the concentration of alcohol. So basically, if someone is drinking, and obviously you should not do this, but if someone is drinking and driving, okay, they can detect the ethanol, which is the alcohol in the drinks, and they can detect this OH bond here. The more intense that absorption is, the higher the concentration, and then they can tell you whether you're over the limit or not.